Good morning, and thank you, and many thanks for the invitation. It's an honour and a privilege and a learning experience for me to be here. Okay, so I've broken this presentation into 4 sections. Each of the sections is actually quite light. The first section, I'm going to talk about what I call the power IoT ecosystem. So we talk about energy harvesting for IoT, so taking ambient energies such as light, vibrations, heat, RF energy, and using these to solve power sensors. So a lot of people do not understand what we call the power IoT challenge. And really it's all about trying to make the batteries ideally last indefinitely, but how do we make them at least outlive the application that they're serving? And there are 3 ways we can do this. The first one, and the obvious one, is that we design and we manufacture batteries that supply more energy to us. The second way we go about this is reducing the power consumption of the IoT device. And this is where I spend a lot of my time, understanding the applications and how can we really work together to reduce the power consumption of the wireless sensor. And the third one then is, of course, energy harvesting, the use of ambient energies. So we can, either use ambient energies or use wireless power transfer. Take these ambient energies and use these as an auxiliary power source to ultimately self-power these sensors. And this is where my group, ICT for Energy Efficiency, works. There are other people in Tyndall. Tyndall is an organisation, we're a research organisation in Ireland. We're almost 700 people. There are people in Tyndall developing micro batteries based on nanotechnology, but my own group focuses on the power management and the system integration of these devices. Okay, and we'd like to believe that we've brought some thought leadership to this whole ecosystem over the last number of years. I know this is a bit of an eye chart that you see here in front of you, but let me just point out the main message here. Yeah, the pointer works. So you can see here, this is a spectrum of power consumptions of various IoT devices here, going from nanowatts all the way up to megawatts. And what we have done is we have zoomed into the area that I show here. This is the kind of area where we believe there are opportunities for us to take real-life ambient energies in the region of maybe 1 microwatt up to a couple of hundred microwatts. And you can actually self-power sensors. And again, we've given some references there, that a 50 degree C temperature gradient with a thermoelectric array, a 200 millimeter cubed indoor solar panel, a 5 degree C temperature gradient, these a vibration device running off just 0.1 G. All of these give us power ranges in these areas with reasonable size components that are relatively easy for us to retrofit. So a big part of our work really is trying to work with people like the people in the room here today to try and see, can we come up with sensing solutions whereby the average power consumption of these devices is down in this region? Now, I say average power. Many of the sensors we know will consume a lot of power, but if we can turn these devices off for long periods or reduce the communication infrastructure associated with these, in many applications it is possible for us to get down to this region. There's a white paper associated with this. I was the coordinator of this project. It's called Enables. The link is there. I'd encourage you to go and look at this if you want to understand the thought process behind this in more detail. Okay, so this kind of brings us then to the ecosystem that I've been trying to develop over the last 13, 14 years here. And when we talk about energy harvesting, this is what traditionally people think about, technologies. So energy harvesting technologies, energy storage, micro power management, and the system integration of all of these. And what we're trying to do there is serve the various IoT applications. So we have Industry 4.0, renewable energy, smart mobility. We have utilities, which is what we're talking about here today. And then we've got various applications in the home and so on. And of course, what we need to do then is we need to talk to the various stakeholders, not just the developers and the suppliers, but also the users and the system integrators of these technologies. So how do we get from that inner layer to the outer layer? Well, what I've been preaching for the last number of years is that we need what I call enabling technologies, okay? What we need to do is we need to bring in complementary technologies to these technologies so that we can mix these technologies with the core technologies here to serve these applications. And again, the Enables position paper that we wrote that I referenced in the previous slide will give you a good insight to what we're talking about here. And, I found this throughout my career. It's Pareto, all right? 80% of the optimization opportunities here at the early conceptual stage. So projects like H-Hope are very, very important for us to make sure that at the early stages, we understand where is the opportunity to optimize the power consumption and optimize the use of energy harvesting in the sensors so we can make them as small and unobtrusive as possible. Okay? So one thing that we are doing in a project called Connect, this is a Research Ireland infrastructure, is developing test beds. So people can talk about the theory of the power consumption of these wireless sensors, but ultimately in many cases it's very difficult to extract that from data sheets. So what we need to do is we need to develop a test bed based on energy harvesting, and we see in a real-life application, how do we minimize the power consumption? How do we maximize the use of ambient energies? How do we bring stakeholders together to figure out how do we minimize the power and maximize the ambient energy and ultimately self-power these devices? And the beauty of this is that this is running for 6 or 7 years and hopefully will run for another 4 or 5 years plus. We're not bounded by a particular project that might run for 3 or 4 years, that we can transcend the boundary that we traditionally have in projects in terms of scope, timeline, and so on. It also leverages a concept that we have in Tyndall. We've come up with a concept called an ESIP, Energy Source and Package. So effectively, it's a solution whereby we can either replace or augment the function of the battery, effectively using ambient energies that will supplement the operation of a battery in a real-life application. And really, we are collaborating not just at the node level, but also at the network level. We're trying to find ways here to reduce not only the node power, but also the network power as well. Network power is also going to be a problem if we've millions or billions of these sensors all connected together. It's going to put a huge strain on our electricity grid. Okay, so one area where I've been prominently involved is in a workshop called NRHarv. So this is something that I set up with a colleague of mine 8 years ago at this stage. And the whole idea here was to bring together an ecosystem of stakeholders, such as I showed in the previous slide here, and try and get all of the stakeholders working together, not just in the core technologies, but in the applications and the integration here as well. What we're trying to do there is build an ecosystem of experts working together to share knowledge, best practices, to foster early collaborations, minimize power consumption, and efficiently use the ambient energies that's available. The latest NRHarv was last year, not too far away from the beautiful city of Perugia. So this is an event whereby we had 86 people attend, and we got a high degree of success here, a high percentage of industry content here as well. And all the proceedings of this are publicly available online as of last month. Okay, so the whole idea is that what we learn here, we share with the entire community. Okay, so that's kind of the overview. That's kind of a lot of the work that I've been doing at a high level over the last number of years. A bit more detail then about some of the technology platforms that we've been developing. This is the ESIP I mentioned a few minutes ago, trying to integrate various energy harvesting, energy storage, and micropower management solutions together into an integrated package. And by the way, it's not just the electronics. We also need to look at the packaging, the embedding, the various types of manufacturing processes we need to manufacture this part as well. So I have an example here on the next slide of one that we've actually developed. This is a self-powered smart patch. So this is something you can put on your arm. It can take the temperature from your arm, and with a 35 degrees C temperature, which is what you'd get from a typical body, it's possible to develop a self-powered tag that can take a Bluetooth reading every 78 seconds. Now, the small print here means that we do need a significant amount of airflow to get this to work. So we're doing work on simulation models to see how do we reduce the amount of airflow that we need here as well. And indeed, how do we guide people to develop better thermoelectric generators for us? But it gives you an idea as to the value of system integration, not just developing technologies in isolation. Okay. Another important tool that we've developed is a simulation model. So if we take all of the various components we need in a wireless sensor, we have a power source, we've got a wireless sensor node, we've got some sort of ambient energy source, in this case a PV panel. We need to store the ambient energy in something called a supercap, like a secondary battery. And what we can do is that with this simulation tool here, we can put in the start and the end times, in fact, the durations whereby the light energy is available. We can put in the lighting levels, and we can simulate the charge-discharge profile on this supercap. And the whole idea here really is that we need to keep this voltage here above the minimum threshold for the wireless sensor node to work. So you can see here the green line is the light going on and off. You can see when the light is on, the supercap is charging. When the light goes off, it discharges. You can see very good correlation here between the simulated results and the actual results. It also gives you an indication that if we lose light for, say, 1 day or 2 days, how long is it going to take before we go down to a voltage whereby we no longer have enough power to self-power the device. So I do believe that simulation tools like this are going to be very, very important system integration tools for people to make sure that they design and they scale the components here for self-powering. We are using this on 2 EU projects, a project called Energy ECS, which finished recently, and one called Lollipop IoT, which is active at the moment. I'm the technical coordinator of that project. Okay, not going to go into detail here, but what we're also developing in Tyndall is silicon. That's one of our departments within Tyndall. We are developing an energy harvesting IC that can take multiple types of ambient energies, can take a wide input, a number of input voltages. We can step up or step down the voltage to give usable energy to power these wireless sensors. And the beauty behind this platform here is that if somebody comes to us with a new application, we can use the existing silicon and modify it or create a new circuit block. So we can develop new silicon probably at about 30% of the traditional time associated with developing new silicon. So we believe this is another very important platform for us to accelerate the development of technologies that enable us to self-power these systems. Okay, I mentioned the testbed earlier on this presentation. A little bit more detail on this. This is a collaboration with Trinity College Dublin, who lead the overall Connect Centre. So the whole idea behind this is that we take off-the-shelf parts, either Arduino parts or parts from STM that already have a lot of the functionalities that we need built into them. So they have various types of energy harvesters, a power management IC, microprocessors and sensors, and then Bluetooth technology. And the whole idea really is to build a real-life testbed around these parts. This is the one that we use as our starting point. It's called an Arduino part. It has got all the functionalities that are listed there. So all of these can be configured, how often you want to sense, what you want to sense, how you communicate using Bluetooth, to a gateway or to the cloud. But we are developing this in an agnostic way, that we're also developing it using ST micro parts here as well. And indeed, we are going to add other types of parts here as well. The reason why we're using off-the-shelf parts is that people very often want to build 20, 30, 40 of these, and we don't want to be developing so many of these parts based on our own platform. This is how it works. So we can either program the Arduino or the STM part, or any part that anybody gives us, either as what we call a slave node, so it's like an edge node that receives instructions, or as a master node. The master node interfaces then to maybe the cloud or to a gateway, and then the slave nodes do what they're told. And the whole idea here is that we put in various hooks, what I call software hooks here, so that we can try and figure out how do we optimize the rate at which we sense, the rate at which we communicate. When do we sense, for how long, and when do we actually process, and where do we process that data in an energy optimized way, taking into account the limited energy that's available at the node and the limited available energy available at the gateway and the cloud. So I just go back here. This is just showing you visually what the tool looks like. So we can look at the ambient energies. We can program in various sensing intervals. We can look at what type of sleep intervals we use for the sensors and so on. And this will enable us then to figure out whether we can self-power these devices or not. Okay. If you look under the hood of a wireless sensor, different power levels are consumed at various levels. For example, a sensor might be asleep. When it starts up, it will consume a certain amount of power. When it's in startup mode, then it tries to handshake. It goes into advertising Bluetooth mode. Then it starts processing and transceiving data. And as you can see here, we go from milliamps down to microamps here, depending where we are. So it's really important for us to understand what's this overall power and energy signature so that we can optimize this based on the application need. Okay, almost there. Some relevant EU projects. One is called Lollipop IoT. This is one that I coordinate myself. The whole idea here is that we look at a number of real-life industry applications, and we develop various technologies here to serve these applications. They relate to asset tracking, condition monitoring, and energy efficiency optimization in buildings. We have 10 countries, 42 partners, almost 30 million euros there as a budget. This kind of shows you the various use cases we have. So as I said, asset tracking, condition monitoring, energy efficiency optimization. Each one of these is developing either self-powered or wireless sensor solutions which have at least 10 times longer battery life than conventional applications. I'm happy to talk about these with anybody who's interested during the break. Okay, finally, Rise Energy project. This is an EU research infrastructure project that Giovanna and I are working on. The whole idea here is that we're bringing together stakeholders who are developing technologies in each one of the areas here, for example, PV, hydrogen, integrated grids, energy storage, and so on, and open up our doors to our people and to our infrastructure so people can do experiments and see how can we mix and match these technologies and increase the uptake of renewable energy systems in Europe. Okay, it's a project that started March last year. We have a thing called a transnational access call. This is the free of charge access program. We just opened our second call at the moment, which is open for the next 3 or 4 weeks, whereby with a very simple application form that we will have 3 or 4 pages, you can apply to gain access to any one of the facilities here with the core competencies in this area, and they can do a feasibility study for you to try and see can they take your technology or can they serve your application need related to renewable energy systems. Okay, so it's all about building an ecosystem of stakeholders who have expertise in various areas. It's based on various previous research infrastructures in various areas, including PV, hydrogen, energy storage. The Enables is the ICT one that I was involved in related to energy harvesting. Ascent is another Tyndall one that's related to nanotechnology and flexible electronics. Okay, these are the 10 target areas we have in Rise Energy. This is the area that I lead, so I'm looking to try and see how can we retrofit wireless sensors in applications related to many of these technologies. So a big push here on cross-cutting technologies, merging these various technologies together in a system integrated way. Okay, so in some sense, it's similar to the HO project, but it's got a broader focus. Again, it's all about retrofitting wireless sensors on, in or near renewable energy systems. And I think the big opportunities here are doing condition monitoring or energy efficiency monitoring of equipment, and also improving the interoperability between various components so that we can be cleverer about how they interact together and we optimize the energy that's available in terms of transmitting it, storing it, and actually using it. The sensors can be put in temporarily or permanently at the development point. We can do simulation models for you. We can do retrofitting of the sensors in a laboratory type environment. If you've got access to an environment there as well, we'd be more than happy to explore that as well with you. Okay. Okay, and last one is, there's a very similar infrastructure called InfraChip. Same idea as the Rise Energy project, but it's focused really on powering, sensing, thinking, and connecting. So it's broader in scope. Various technologies available here from the partners here. It's coordinated by us in Tyndall. So my interest area here, of course, is powering. So again, if somebody wants to do a feasibility study associated with retrofitting wireless sensors and they want them to be self-powered for any application, I'm interested in working with them to try and see, can we do these free of charge feasibility studies? Okay, and that's my area. Just an example of the research infrastructure that's available. This is what I'm offering. I'm offering the ability to do these ESIPs. I'm offering the ability to do simulation models based on our PMIC, and also using our testbed associated with this. I think this is the final slide. All of the test beds and platforms I've talked about are available through the InfraChip and Rise Energy Transnational Access programs. These are some that we already have underway at the moment. These are 3 that we're doing in InfraChip. We're doing a PMIC circuit for PV arrays, energy harvesting powered system on chip, where we minimize the size of the energy harvesting components, and a simulation model for extreme environments for supercaps. The first Rise Energy Transnational Access program under ICT has been approved and will start soon. And it relates to a wave generator data acquisition unit. These data acquisition units typically only last a few days. We want to get the battery life up to a few months, or maybe even self-power them if we do that. And the main reason why I'm here today is that if anybody is interested in InfraChip or Rise Energy and is interested in doing a free of charge study, come and talk to me during one of the breaks. Okay, so that's it. Thank you. Gora Mahagut. That's the way we say thank you in Irish. Thank you for your time.